The F-100 Super Sabre should have been impossible for its time. In the early 1950s, most fighter jets were still struggling to behave near the speed of sound. Pilots described shock waves like invisible walls in the sky. Aircraft would shake, controls would feel unpredictable, and pushing too hard often ended badly. Engineers were still trying to understand how air changed as speed increased. Then North American Aviation introduced a fighter that did something nobody felt comfortable with. It did not just break the sound barrier briefly in a dive, it stayed there. The F-100 became the first United States Air Force fighter capable of sustained supersonic flight in level flight. That detail sounds ordinary today, but in 1953 it felt reckless. Most jets could dip past Mach 1 for a moment. The F-100 could cruise there. And that is where the real problem began, because everything engineers believed about airflow, stability, and control started behaving differently when an aircraft remained supersonic for more than a few seconds. The rules they trusted suddenly felt incomplete. The F-100 did not break physics. It exposed how little we understood about it at the time, and its speed forced the entire aviation world to catch up very quickly. Today, breaking the sound barrier sounds routine. In the early 1950s, it felt unpredictable and dangerous. Pilots who pushed toward Mach 1 described shaking, strange control responses and airflow that behaved in ways nobody fully understood. Shock waves formed over the wings and fuselage, changing lift and drag suddenly. Controls that worked normally at lower speeds felt heavy and unreliable. Most jets treated Mach 1 like a boundary you crossed briefly in a dive, then escaped from quickly. Aircraft were not built to stay there. Structures, wings, and control systems were never meant to handle sustained supersonic airflow. The F-100 was. Once it remained past Mach 1, engineers realized something important. Supersonic flight was not simply faster flight. It was a different environment entirely. Shock waves stayed attached to the aircraft. Lift changed. Drag increased in ways that had not been predicted. Pilots experienced sudden pitch-ups at high speed, later called the Sabre dance, and control sensitivity that could change without warning. What looked like a speed milestone was actually exposing how little engineers understood about sustained supersonic flight at the time. The F-100 forced aviation science to catch up with reality. The F-100 did not look radically different from earlier jets at first glance, but its shape was built around a new understanding of airflow. Engineers realized that once an aircraft stayed supersonic, air no longer flowed smoothly over the wings and body. Shock waves formed and stayed attached, and those shock waves had to be managed rather than avoided. This is why the F-100 used a swept wing design with thin airfoils and a carefully shaped fuselage. The goal was not just to reduce drag, but to control how shock waves formed and where they traveled. The aircraft's nose, wings, and tail were all designed to guide airflow in predictable ways so that supersonic flight would not turn into a constant battle against instability. Even the placement of the air intake mattered. At high speed, air entering the engine could create its own shock patterns that interfered with performance. The F-100's intake design helped stabilize airflow before it reached the engine, allowing the jet to maintain thrust in conditions where other aircraft would struggle. This design approach was new because engineers were no longer designing for what happened below Mach 1. They were designing for what happened after it. The aircraft was shaped for a region of flight that most jets still treated as temporary. That is why the F-100 could remain supersonic while others had to slow down. It was not simply more powerful. It was designed specifically for a different kind of air. And that decision set the stage for both its success and its challenges. Speed is never only about shape. It is about thrust. And the F-100 had more of it than most aircraft of its time knew how to handle. The Pratt & Whitney J57 engine was one of the first powerful enough to push a fighter into sustained supersonic flight, not just a brief dive past the sound barrier. That raw power is what allowed the aircraft to remain beyond Mach 1 instead of slipping back below it like earlier jets. But that same power exposed new problems. At high speed, air entering the intake was already compressed and heated, and if airflow became unstable, the engine could surge or lose efficiency. Pilots quickly learned that throttle control mattered as much as airspeed because pushing the engine too hard could create situations the aircraft was not fully prepared to handle. The J57 gave the F-100 the ability to live in supersonic flight, but it also showed that more thrust did not simply make an aircraft faster. It magnified every aerodynamic issue that came with sustained speed and forced both engineers and pilots to learn how to manage that power safely. As the F-100 spent more time beyond Mach 1, pilots noticed something unsettling. The aircraft did not always respond the way it did at lower speeds. Small control inputs could have large effects, and sometimes the jet seemed to move on its own without warning. This was most visible in the phenomenon later called the saber dance. At high speed and certain angles, the nose could pitch up suddenly and violently. Recovery required precise inputs and calm reactions because overcorrecting could make the situation worse. What pilots were experiencing was not a flaw in the aircraft, but the result of airflow behaving differently in sustained supersonic conditions. Shock waves stayed attached to the wings and tail, changing how lift was produced and how control surfaces worked. The faster the jet went, the more sensitive these effects became. Engineers began to realize that control at these speeds was not about strength, but about understanding how air moved once it crossed into this new regime. The F-100 forced both pilots and designers to learn that speed did not just affect performance. It changed how the aircraft behaved entirely. Before the F-100, supersonic speed was something pilots touched briefly, then left behind. Missions were planned around the idea that aircraft would spend most of their time below Mach 1, using short bursts of speed only when needed. The F-100 disrupted that thinking because it could remain supersonic in level flight for extended periods. This changed how distance, timing, and response were understood. An aircraft that could cruise faster than sound could reach targets sooner, reposition quicker, and leave an area before opponents could react effectively. Speed stopped being a momentary advantage and became a constant part of how the aircraft operated. It also changed how threats were perceived. Interceptors and defenses built around subsonic and transonic assumptions suddenly faced something that could outrun expectations. Radar operators had less time to track. Pilots had less time to respond. The pace of encounters increased simply because the aircraft did not need to slow down. The F-100 showed that staying supersonic was not just a performance milestone, it quietly reshaped how air operations worked. As the aircraft began spending long periods beyond Mach 1, something unexpected became clear. The F-100 was not simply faster than earlier jets. It was faster than the systems designed to respond to it. Radar stations, interceptor squadrons, and ground defenses were all built around a certain rhythm. Detect the target, confirm the track, pass the information along, then react. That rhythm depended on time, and the F-100 started stealing that time away. Radar operators were trained to track aircraft based on movement patterns they understood. Interceptors were launched using projected paths calculated from known speeds. Ground defenses relied on the assumption that once a contact was detected, there would be enough time to classify it, communicate the information, and organize a response. The entire defensive chain depended on predictable timing. The F-100 disrupted that timing without trying to. When the jet remained beyond Mach 1 for extended periods, it crossed distances much faster than defensive systems were used to handling. By the time a radar return was confirmed and passed up the chain of command, the aircraft had already traveled far from its original position. Predictions that worked well for slower aircraft suddenly became unreliable. Interceptors often found themselves racing toward where the F-100 had been moments earlier rather than where it actually was. This created a growing gap between detection and reaction. It was not that radars could not see the aircraft. It was that the information they gathered became outdated almost as soon as it was processed. Speed reduced the usefulness of that information. Ground-based defenses ran into the same problem. Calculating an intercept solution depended on knowing how fast a target could travel and where it would likely be in the near future. When that target remained supersonic instead of slowing down as expected, those calculations lost accuracy. Reaction times shrank, margins for error disappeared, and defensive planning had to adapt to a pace it had never been built for. The F-100 did not defeat defenses through stealth or advanced electronics. It did so by simply moving faster than the system's ability to think, forcing an entire generation of air defense planning to evolve around a new reality where speed itself had become a strategic advantage. The F-100 did more than fly fast. It forced aviation to grow up in a hurry. By proving that a fighter could live beyond Mach 1 instead of just touching it briefly, the aircraft exposed gaps in knowledge that engineers could no longer ignore. Aerodynamics, control systems, engine behavior, materials, and pilot training all had to adjust to a new reality where supersonic flight was not an exception but a normal operating condition. What had once been treated as a dangerous boundary became a place where an aircraft could actually work, maneuver, and fight for extended periods. This shift did not happen quietly. It had ripple effects across the entire aviation industry. Engineers began to study shock waves with far more urgency, not as strange side effects of speed, but as powerful forces that shaped how an aircraft had to be built from the ground up. Wing shapes changed to manage airflow more predictably. Fuselage designs evolved to reduce unwanted pressure buildup. Air intakes were redesigned to keep engines stable at higher speeds. The goal was no longer simply to survive brief contact with supersonic airflow, but to understand how to operate within it safely. Stability issues like the Sabre dance stopped being pilot stories shared in ready rooms and became engineering challenges that demanded real solutions. What pilots experienced in the cockpit turned into data that reshaped wind tunnel testing, flight modeling, and design philosophy. The strange behaviors observed at high speed were no longer treated as quirks of a single aircraft. They were treated as lessons about how air behaves once the sound barrier is left behind. The F-100 made it clear that sustained speed required a deeper understanding of airflow than anyone had previously developed. Engineers began to rethink how control surfaces worked at high velocity. They studied how shock waves attached to wings and tails. They refined how aircraft could remain stable when lift and drag behaved differently than expected. This knowledge did not stay with the F-100, it became part of the foundation for every supersonic fighter that followed. Future aircraft benefited directly from these lessons. Fighters that came after the Super Sabre, including jets capable of even greater speeds, were designed with a clearer picture of what sustained supersonic flight actually meant. What seemed unpredictable and dangerous during the F-100's early years gradually became part of standard aviation knowledge because the aircraft had already ventured into that territory first. The F-100 did not break physics. It revealed how incomplete our understanding of speed really was at the time. By operating where others hesitated to go, it forced the science to catch up. That is why its speed still feels impressive today. It was not just fast for the 1950s. It was ahead of the knowledge meant to explain it, and it helped shape the future of supersonic aviation for decades to come. If you enjoyed this breakdown and want more stories like this, make sure to like the video and subscribe to the channel. There are many aircraft whose speed changed history, and we will be diving into more of them soon.